Welcome to Pure Facts, where we explore the mysteries of the universe, unravel the secrets of science, and take you on a journey from the Big Bang to the present day. If you're curious about the cosmos, evolution, or how everything came to be, you're in the right place. Have you ever stopped to wonder, where did all of this come from? The stars, the galaxies, even life itself? Today, we're embarking on an adventure like no other, back to the very beginning of time itself. From a point smaller than an atom to the birth of everything you see around you. The first 11 phases of the universe are filled with epic explosions, mind-bending expansions, and forces beyond our imagination. So buckle up. This is going to be an unforgettable ride. It all starts with the Big Bang, the event that marks the beginning of our universe, over 13.8 billion years ago. Imagine everything, every atom, every star, every galaxy, compressed into a point smaller than an atom. No space, no time, just an infinite density of energy. And then, in an instant, boom! The universe explodes into existence. Space itself stretches outward at incredible speeds, and for the first time, time begins to tick. The Big Bang wasn't an explosion in space, it was an explosion of space. And while this moment gave birth to everything, it was also the beginning of some of the most fundamental questions that physicists and cosmologists still wrestle with today. What caused it? Why did it happen? Some suggest that it was a random quantum fluctuation. Others believe our universe is part of a larger multiverse. What we do know for sure is that this is where the cosmic clock starts ticking, and the universe will never be the same again. Now, we enter the Planck era, the first 1043 seconds after the Big Bang. This is a time so extreme that the very laws of physics break down. All four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, are fused together in a single superforce. The universe is unimaginably hot and dense, and space itself is constantly warping and shifting. This moment in time is named after Max Planck, the father of quantum theory, and it's here that we encounter a problem. The physics that work in the universe today just don't apply. We need a theory of quantum gravity, a framework that merges the strange microscopic rules of quantum mechanics with the vast cosmic power of gravity. For now, this era remains a mystery, one that keeps physicists up at night as they try to unlock its secrets. Next, we enter the grand Unification Epic from 1043 to 1036 seconds. During this phase, gravity breaks away from the other fundamental forces. It's the first force to go solo, and this will shape the universe forever. With gravity now acting on its own, space begins to expand more smoothly. Meanwhile, the other forces, electromagnetism and the nuclear forces, remain unified for just a bit longer, but they too will soon split apart. At this point, the universe is still unimaginably hot, with temperatures reaching over a quadrillion times hotter than the core of our sun. Particles are zooming around at near light speed. Though it's hard to imagine the chaos happening on this tiny scale, this separation of forces is setting the stage for the creation of the first matter. Now comes the most dramatic moment yet, the inflationary epoch. Around 1036 seconds after the Big Bang, the universe undergoes a mind-boggling expansion. So fast, it's almost impossible to comprehend. Imagine this. The universe grows from the size of an atom to the size of a galaxy in less than a trillionth of a second. Faster than the speed of light, faster than anything you can imagine. This expansion is driven by the mysterious inflaton field, which causes space to blow up like a balloon. Why did this happen? That's another mystery, but what we do know is that this rapid inflation helped smooth out the universe, eliminating tiny irregularities and preparing it for the formation of stars and galaxies. By the time inflation ends, the universe is massive, smooth, and much cooler than it was just moments before. This was one of the most important moments in cosmic history. Without inflation, the universe might not look anything like what we see today. As inflation winds down, we enter the Electro Epic from 1032 to 1012 seconds. Here, the electromagnetic force and the weak nuclear force separate. We now have distinct forces governing how particles will interact. In the chaos, tiny particles begin to form: quarks, leptons, and other building blocks of matter. The universe is still a swirling soup of energy, far too hot for atoms to form, but it's beginning to cool enough for the first interactions between particles to take place. These tiny quarks will one day come together to form protons and neutrons, which will go on to make up the very atoms that build stars, planets, and you. The temperature in the universe at this point is still unimaginably high, around 10 quadrillion degrees. But as the universe expands, it cools slightly, allowing the next major phase of particle formation to take place. Welcome to the Quark Epic, from 1012 to 1006 seconds after the Big Bang. The universe is a roiling, chaotic sea of quarks and gluons, elementary particles zooming around at incredible speeds. These quarks are the building blocks of protons and neutrons, but right now, they're far too energetic to stick together. Everything is in constant motion, with particles colliding and bouncing off each other like tiny cosmic pinballs. At this point, the strong nuclear force, which will eventually bind these particles into atoms, is starting to take effect, but the temperature is still too high for it to work. The universe needs to cool down just a little more for the first atomic particles to begin forming. Now we enter the Hadron Epic, 1006 seconds after the Big Bang. As the universe cools, quarks finally begin to bond, forming protons and neutrons, two essential building blocks of atomic nuclei. These particles, called hadrons, will eventually make up the atoms that create everything in the universe. But it's not smooth sailing just yet. A cosmic battle between matter and antimatter rages on. For every particle of matter, there's an antimatter counterpart. When they collide, they annihilate each other in bursts of energy. But luckily, there's a slight imbalance. Just enough matter survives to form the stars, planets, and galaxies we see today. Without that tiny edge, none of this would exist. We now enter the Lepton Epic, which lasts from 1 second to 10 seconds after the Big Bang. At this point, the universe is dominated by leptons, such as electrons, flying around in a hot, dense plasma. Although protons and neutrons are already present, it's still too hot for them to combine with electrons to form atoms. Meanwhile, neutrinos, ghostly, nearly undetectable particles, are streaming out in every direction. These neutrinos don't interact much with matter, and billions of them are passing through your body right now without you even noticing. As the universe expands and cools further, electrons will eventually begin to combine with protons, but we're not there just yet. The universe is still chaotic and extremely energetic, but this phase sets the stage for the formation of atoms and the release of light in the coming epochs. The Photon Epic spans from 10 seconds to around 380,000 years after the Big Bang. Photons, particles of light, are everywhere, but they're trapped in a hot, dense plasma. At this stage, the universe is too energetic for electrons to bond with protons, so free electrons keep scattering the photons in all directions. Light particles are stuck in a chaotic, radiant soup, unable to travel far. The universe is essentially opaque, like a dense fog of energy. As the universe expands and cools, these free electrons will eventually combine with protons to form neutral hydrogen atoms. When that happens, light will finally be able to travel freely through space. This will mark a major transformation, turning the universe transparent and allowing photons to stream across the cosmos, leading to what we know today as the cosmic microwave background. Now we've reached the Recombination Era, about 380,000 years after the Big Bang. The universe has cooled enough for protons and electrons to combine into neutral hydrogen atoms. This marks a key transformation. For the first time, light can travel freely through space. Up until now, the universe was like a glowing, dense fog, with light particles trapped in constant collisions. But as atoms form, this fog clears, and photons, particles of light, are free to stream across the universe. This is when the universe becomes transparent. This newly released light is still detectable today as the cosmic microwave background, CMB. It's like the universe's baby picture, showing us what it looked like just 380,000 years after the Big Bang. These ancient photons provide a glimpse into the early cosmos, revealing its first structures and patterns. It's one of the most important tools we have to study the birth of our universe. And now, the universe enters a long, cold period known as the Dark Ages. This period lasts from 380,000 years to around 200 million years after the Big Bang. The universe is filled with neutral hydrogen, but there are no stars, no galaxies, just vast, dark clouds of gas. The only light is the faint afterglow of the cosmic microwave background, still lingering from the Recombination Era. The universe, for all its potential, is in darkness. Temperatures are dropping, and matter is slowly coming together under the pull of gravity. But it will be millions of years before the first stars flicker into existence. During these dark ages, matter is quietly organizing itself, forming the first large-scale structures. Tiny ripples in the fabric of space that originated during inflation are slowly becoming denser. These regions will eventually collapse under their own gravity, creating the seeds of future galaxies. It's a quiet, eerie time, a cosmic waiting game. And that, my friends, is just the beginning. From the explosive birth of the Big Bang to the eerie silence of the Dark Ages, the universe has already come a long way. But the story isn't over yet. Soon, the first stars will ignite, galaxies will form, and the universe will light up in ways that will blow your mind. Join us in the next episode as we explore how the universe goes from darkness to light. Until then, hit that subscribe button and stay tuned, because the story of the universe is just getting started.